Okay, so today we're going to talk about uncertainty in a single input measurement set. So let's imagine for a second that I have some 5-gram weight, and its calibration weight comes from a company. I know it's 5 grams, exactly 5 grams. And I also have 2 models of scale. And I want to evaluate these 2 models to see how accurate they are. So I can put my 5-gram weight on each scale and then take it off and then put it back on again, and take it off and put it back on again, and record those values. And if I did that, I might get something that looks like this. And there's a little mistake here. I want to call each measurement of weight X, and I want to call the measurements that come from model A, XA, and the measurements that come from model B, XB. And so I weigh the 5-gram weight 6 times on each scale. And XA creates the red measurements, and XB creates the green measurements. And so I can see straight away that I get values that are fairly close to 5 grams here, as compared to model B, where I'm getting kind of a larger spread. My minimum was 2.1, my maximum was 7.0, and here my min and max are closer to 5. So to get an idea of how that data actually spreads out, I could plot those values on a number line. And so here I plotted the red values with little red x's and the green values with little green x's. Let me just move this up to give myself a little more room. And so what I could do is I could draw some bins, and I could say, okay, I'm going to have a bin that spans some set of the number line, and then I'm going to plot how many data points fall in that bin. On a bar chart. And I can choose the width of the bin to be whatever I want. So let's say I choose something like from here to here. Well, in this bin there's 2. So I would draw a bar corresponding to a height of 2. It's green. Then I go to here, and I'd have 1. And then I go to here, and also have 1. And then I go to here. These should all be the same width, roughly speaking, to the best of my ability. And I've got 0 here. And then I've got 1. Okay, and for the red, I'd come in, I'd use the same bins, so I'm comparing apples to apples. I'm going to draw it a little squiggly so you can see it. I've got 1 in this bin. And I've got 3 in this bin. And I've got 2 in this bin. And so why did I do this? Well, I did this because the red X's are helpful, but I can't see exactly how they stack up. And so by creating these bins, I can get an idea of how that data is distributed or concentrated along that number line. And so I see this meshes with my understanding from looking at the numbers that the red scale, model A, makes a tighter sort of grouping of data than the data from model B. So if I took a bunch more measurements, let's say 20 or 21 measurements on each scale, I could put that in a spreadsheet in Excel, and I can get a good look at that data. So I'm going to pause for a second and bring that up. So I might get something in Excel that looks like the following. I've got a sample number column, I've got a weight from A and a weight from B. These are in grams. This is a number of the sample. So here I've got 21 samples, and I've got all of my data here and here. And what I would kind of want to know is, what is the average from those data sets? Oops. And I have it calculated here. Just hide it. Maybe. Unhide. No. There we go. So I've got 21 samples. And so you can see here that, let me just move it down a little bit. You can see here that I've got an equal sign, which says I'm going to put in a formula, and I'm going to take the maximum of A3 to A23. So that's right here, A3 to A23. So I want the number of samples, and the number of samples is the maximum value of that column. So I've got 21 samples. And then I want to compute the mean of, XA, not X1. And in this case, I'll put equals. Average is the command formula for computing the mean. And in this case, it's the range from B3 to B23. That's right here. And so if I wanted to calculate that, I would just type in equals average. I would open parentheses, and I would click on B3 and drag down to B23, close my parentheses, and push enter. And then I get my mean. And what I note is that Model A and Model B both have the same mean. So that's good. It means I'm pretty accurate in the sense that I am getting good repeated, a consistent value of the average between the two models. What I know, though, is that those data are pretty far apart for the green model, Model B, and they're grouped pretty closely together for Model A. And so I'm thinking I would choose Model A because if I'm going to rely on a single data point sometime later, there's a better chance for Model A that I'm going to get closer to the actual mean value, not necessarily the real value, but the mean value. And so what I do to get an idea of this is I'm going to take I'm going to examine a statistical quantity called the standard deviation. And so before I do that, I want to just show something else from the PowerPoint there. So we could imagine if I took many, many, many data points, and I kept building smaller and smaller and smaller bins until my bins were basically touching, and I had what sort of looks like a curve, I could end up with something that looks like this. This is a standard Gaussian curve. So standard Gaussian curves appear often in measurement systems. So what's happening is the data is sort of falling within this shape of a distribution about some mean value. In this case, that mean value is shown as mu. And for a Gaussian curve, about 34% of the data falls within 1 plus minus 1 to plus 1, sorry, minus 1 to mu, or mu to 1. Each of those bins contains about, or ranges I should say, contains about 34% of the data. So in total, 34 plus 34 is 68% of the data for a random Gaussian distribution will fall within plus or minus 1 standard deviation. Then within 2 standard deviations, we pick up another 13% and another 13%. So 68 plus 27 is about 95% of the data will fall within plus or minus 2 standard deviations. And then once we get up to plus or minus 3 standard deviations, we've got over 99% of the data. And so we see that this standard deviation can be a really nice measurement to show how much data is going to fall within that range of plus or minus 1 or plus or minus 2 standard deviations. So if this is true, how are we going to calculate a standard deviation? And so I'm going to introduce some statistical terminology, and then we'll go back to our data set and calculate what the standard deviation is for our 2 measurement systems. So we talked about a mean. We sum up the total data points. We divide by the number of data points. You should have probably heard about a statistical quantity called the median. The median is different than the mean. The median is if we sort the values from highest to lowest, the median is the value that lies in the middle. The deviation is the difference between a single measurement point and the mean of that data set. Our variance and standard deviation are statistical quantities that we'll look at in a second. And I want to talk a little bit about the difference between a sample and a population. So a sample is the data that you took, and a population is all of the data that exists for that variable. So for instance, if I wanted to measure the height of, let's say, maple trees in the US, that's a good one, I could pick 100 maple trees and measure their height. That's my sample. My sample size is 100. How many maple trees are there in the United States? That's the population. So, I don't know, 10 billion, 100 billion. So, we're going to use measurements from our sample to make inferences about a population. So, when we have a mean, like I said, we add up all of the data samples, we divide by n, where n is the number of samples. The mean, the median, is in a Gaussian standard, in a Gaussian random distribution, is the same value as the mean. However, in a distribution that takes on a different shape, the median and the mean will not correspond. So our deviation is the difference between a single sample and the mean value. And our variance is if we take each of those deviation values, square them, sum them up, and divide by n. So the variance looks like an average of the squared values of our deviations. Why do we square them? Well, if we simply added them up, we'd have some above the mean and some below the mean, and chances are those deviations would sum up to 0. So we want to square them to make them all positive before we go in and take the average. Now you'll notice, if we talk about, oops, I should fix this, this one should be V sub s. So the population variance is the square of all the deviations up to the total population number divided by the number of elements in the population. The sample variance is the square of each of the deviations summed up divided by the number of samples minus 1. And the reason that we need to do that is because in the deviation, we can't get the population mean if we take a sample. We can only get the sample mean. And so we've used up what's called a degree of freedom by calculating the mean value. So we have to subtract 1 to get the true number of independent samples in our variance. And so our sample standard deviation is just the square root of our sample variance. It's similar with the population standard deviation. It's simply the square root of the population variance. So let's go back to Excel and see if we can calculate the standard deviations for our two samples. So here I have two columns, dA squared and dB squared. So what I'm going to do here is I am going to take B3 and I'm going to subtract the mean value for XA, which is down here, and I want that to be the same for every row. So I'm going to put two dollar signs, one in front of the row, one in front of the column, and that will keep that value static. So that when, oops, and I'm going to square it, so I'm going to put it in parentheses, squared. And then when I drag this down, so that my white plus sign turns into a little tiny black plus sign right at this corner, I can drag it down, and that will take each of these values and subtract the mean, because it's static, and then square it. I'll do the same here, except I will do it for the mean, which in this case is the same, because I designed it that way. Okay, so now I can see that when I sum up all of my deviations, I get 9.21, or sum of my deviations squared. I get 9.21 from model A, and I get 984 from model B. Much bigger sum of the deviations. So to get from the sum of the deviations to the variance, I need to divide by the number of samples. Equals this sum of the deviations divided by, so this is a sample, so it's the number of samples minus 1 to get the sample variance. Oftentimes, if your data set is big enough, n minus 1 and n are very similar numbers. So we took 100 data points and divided by 100. Okay, so now that gives us the sample variance. And now, if I want the standard deviation of A, and the standard deviation of B, I would just take the square root of the variance. So I can see that my standard deviation is way smaller for model A than it is for model B. So what would this look like if we were to plot the Gaussian distributions for each of these values? Well, they have the same mean, so they're going to be centered at the same value. Just turn on my drawing tablet here. So they're both going to be be centered at 5.4, but one's going to be much wider than the other. So for instance, the green curve might look something like this. And the red curve might look something like this. And so my standard deviation was, for the red curve, 0.67. So in reality, this red curve would be even more narrow. But for illustrative purposes, we'll say that this is 5.4 plus 0.6. So let's just call it 6. Or sorry, minus 0.6. So it would be 4.8. And up here, it would be plus 0.6. So we get 6.0. And so 67, 68% of the measurements are all going to fall within this range. Whereas, for my Excel, for model B, my standard deviation was 7. That's way out here. Way over here. A little suspect that it's 7, given that our mean is 5. Let me just check this here. Okay, so remember how I said you have to make it static? Didn't make it static for this one. So let's fix our standard deviation value. There we go. So our variance gets to 423. Our sum of deviation gets to 423. Our variance comes down to 21, and our standard deviation is 4.6. That's a much more reasonable value, right? Because if our standard deviation was 7, and we were below our mean value by 1 standard deviation, that would mean the value that we're measuring is negative. And we can't have negative grams. So that's what tipped me off that something was a little bit wrong with our measurement there. And so at 5.4 minus 4.6, we get something like 0.8. And 5.4 plus 4.6 is be something like 10. So you can see that 68% of my measurements are going to fall in a much wider range for Model B than for Model A. So we can see with processes that obey random distributions, Gaussian distributions, we only need 2 numbers to describe the whole shape. We just need the standard deviation and the mean. That's why these are very convenient, because we can talk about how far the data is spread out and where the center of the data is located with just those 2 statistical numbers. And so, oftentimes, we want to quantify the standard error that we would find in our mean value. And we do that using the standard deviation. But we also sort of need to factor in the fact that there were a bunch of measurements taken. And if I take a bunch of measurements, I have a little more certainty in my mean value than if I only took a few. And so our standard error of the mean tells us how certain we are of the mean value. So if a population standard deviation and a number of samples are known, we can calculate the standard error of the mean, which we call alpha, by sigma, the standard deviation, divided by the square root of n. And so typically we don't know the population standard deviation, so we'll use the sample deviation here. And if you take EG207, we'll talk about a little bit more complex way to deal with that. But in general, when n becomes very large, you can see that we start to divide by a large number. And so alpha will go pretty small. If sigma gets very small, since sigma is on the top, alpha will go small as well. And so what is the standard error of the mean in our data? We call it SEM, standard error of the mean. Okay. Be equal to our sample standard deviation divided by the square root of the number of samples. Make that a static A25 up here. When we drag it to the right, we'll get the data applied to this column, but keeping the number of samples the same. This over. So we can see that we have a much higher standard deviation of the mean. Standard error of the mean in model B than we do A. And typically, when we report confidence intervals, what we want is something that says, give me an idea of where, like, maybe 95% of the data will fall. And so oftentimes we'll talk about we'll use plus or minus some value, some number of alpha. And so that's the final thing I want to talk about. So if we're talking about a 68% confidence limit, we're going to take the mean and we're going to plus or minus one value of alpha. And that shows us, that tells us that we have a confidence level of 68%, that the true mean value lies within plus or minus 1 alpha. And if we expand alpha to 2 and 3, we can increase our confidence limits to 95, 99, 99.7%. So that is how we are going to approach single input measurement systems.